Welcome to qnawire.
Okay, we have a list of bases. We have sodium acetate. We have N-butyl lithium. We have sodium amide. We have sodium phenoxide and sodium methoxide. The question is, which of these are strong enough to deprotonate an alkyne? And that's going to have to be a terminal alkyne if it's capable of being deprotonated. Okay, well, and the recommendation is that you use a pKa table to help you. We'll recall that the pKa of an alkyne, depending on species, it varies, is around 25. Okay, so also recall that when we're talking about acid-base reactions and determining if they'll happen or not, what we're talking about is we have an acid and some base, and that those are equilibrium. Sorry, let me write this a little differently. We have an acid, which we'll call HA to denote the proton on A, and some base, which is in equilibrium with the conjugate base of our acid and the conjugate acid of our base. And this equilibrium, K, right, can be approximated or really calculated by looking at the pKa of our acid and what's known as the pKa H of our base. That's what's the pKa of a protonated form of our base, okay? And then calculating this as 10 to the negative pKa minus the pKa-H, or you could say that this is 10 to the pKa-H minus the pKa. Well, in our case, each time our acid that we're worrying about being deprotonated is our alkyne, so about 25, okay? So we're saying if we can find the pKa-H's of, say, N-butyl lithium, which is really the pKa of butane, right? That's the protonated form of N-butyl lithium, which is about 50, right? So if we were to use this formula, we would get, for N-butyl lithium, we'd get 10 to the 50 minus 25, or 10 to the 25, which is a huge number, right? And a huge equilibrium constant implies that the reaction is heavily favored to the right, or heavily favors deprotonation of our alkyne and protonation of, in this case, our N-butyl. Okay, so if we get a number that is greater than 1 out of this formula, that would predict that the base will deprotonate the alkyne, right? And so N-butyl lithium clearly is capable of deprotonating an alkyne, so B is good. The other one off the top of my head that I know for sure is sodium amide, and that's because if you think about sodium amide, the protonated form then is sodium plus and ammonia, right? And the pKa of ammonia that is protonated NH2 is around 35 to 40, depending. And so clearly we would get a positive number out of that from our formula. We'd say 10 to the 35 minus 25 equals 10 to the 10, right? That's like a trillion or something like that, right? So C is clearly strong enough. And then if we look at the pKa of a carboxylic acid, so I'm just jumping ahead there. That's B and C. If we look at A, our carboxylic acid, The pKaH would be the pKa of just any acetic acid, which is less than 25, meaning the pK, it's closer to 17. So if we put that in the formula, it would be 10 to the 17 minus 25 equals 10 to the negative 8, right? That's a very low number. That's less than 1. That means the equilibrium favors the left-hand side, where the alkyne is protonated. That favors the HA rather than the BH side of the equilibrium. And the same is true for the remainder of these, right? So phenol pKa is less than 25. It's close to 20. And methanol, right, the conjugate acid of methoxide, is also less than 25. It's close to 17, right? So the only two that are capable of deprotonating alkyne, because their pKaH is greater than 25, is B and C, which is answer lowercase b.